Hello everyone. Hello everyone. Welcome to my channel Engineering Mathematics 3. I am Supriya Khadke, Assistant Professor, VPK BIT Baramati. So today we discuss the topic integration by part. So that integration by part is useful for the Fourier transform. So how to use that integration by part? So we discuss some result. So result integration u into v is equal to u integration of v minus integration of derivative of u into integration of v. That is the formula for the integration by part. So that u as it is integration of second part, that is integration of v minus integration of derivative of first term, that is derivative of u integration of v. Here we have to use the late formula LEATE we have to use for the u and v. Okay, so now we discuss one problem on that. So that problem is integration u square cos lambda u du. Here suppose u is u square and v is cos lambda u. So that is equal to, as we kept u as it is, so here u is nothing but u square. So u square integration of phi is cos lambda u into du minus integration of derivative of u is nothing but u square, so derivative of u square, again integration of phi is cos lambda u du, bracket complete du. Now here u square is as it is, integration of cos lambda u is nothing but sin lambda u, and derivative of lambda u is lambda, so divide by the lambda here. So that is u square sin lambda u upon lambda minus that integration as it is integration. So derivative of u square is nothing but 2u, so that is 2u, and that integration of cos lambda u is nothing but sin lambda u upon lambda, so that is equal to, now here first term as it is u square sin lambda u upon lambda minus that 2 upon lambda is the constant term kept outside here, 2 upon lambda in bracket that u as it is. So here again we have to use the integration by part, u into sin lambda u. For that we have to use integration by part. So here u as it is, integration of sin lambda u is nothing but minus cos lambda u upon lambda minus integration of derivative of u. So here is u as it is, u integration of sin of lambda u du is equal to, so here first term as it is u square sin lambda u upon lambda minus that 2 upon lambda as it is in bracket that u as it is minus cos lambda u upon lambda as it is minus. So here derivative of u is 1, so 1 into that integration of sin lambda u is cos lambda u upon lambda, so that is minus. So again now here we have to calculate the again integration here. So integration of cos lambda is sin lambda u upon lambda, so that lambda and integration term lambda, so that lambda into lambda here. So we get finally that first term as it is u square sin lambda u upon lambda minus 2 upon lambda and that u in bracket minus cos lambda upon lambda minus sin lambda u upon lambda square. That is the final answer. Again I can repeat the terms here. First term is u square, second term is cos lambda u. Here we have to use UV rule. So first term as it is integration of second term minus integration of derivative of first term and integration of second term. So after calculating that integration, so that u square as it is, integration of cos lambda u is nothing but sin lambda u upon lambda, that minus integration of derivative of u square, derivative of u square is nothing but 2u, and integration of cos lambda u is sin lambda u upon lambda, so that is equal to that first term as it is u square sin lambda u upon lambda minus that 2 upon lambda is constant term kept outside here, 2 upon lambda in bracket. Now here we have to use again integration by part on the term u into sin lambda u. So here u as it is, integration of sin lambda u is nothing but minus cos lambda u upon lambda, that minus integration of derivative of u integration of sin lambda u du, so that is equal to that u square sin lambda u upon lambda as it is minus 2 upon lambda in bracket u minus cos lambda u upon lambda minus, so integration of sin lambda u is minus cos lambda upon lambda. Okay, so that minus minus becomes plus here. So again that integration, take again integration here. So we get u square sin lambda u upon lambda minus 2 upon lambda that u minus cos lambda u upon lambda minus sin lambda u upon lambda into lambda. So again we multiplied by lambda here, we get u square sin lambda upon lambda plus 2u cos lambda u upon lambda square plus 2 sin lambda u upon lambda cube. That is the final answer after multiplying by 2 upon lambda to the whole bracket term. So whole bracket term is whole that term, so that is the whole term. So here get lambda into lambda is lambda square, lambda into lambda, here lambda square into lambda is lambda cube. Okay, so that is the first answer of the that part, integration by part. By using integration by part we get the value of that term. So now next is how to put the value. If suppose integration range is 0 to 1 and that is our final integration answer, by using integration by part we just solve that problem. U square sin lambda u upon lambda plus 2 times u cos lambda u upon lambda square plus 2 sin lambda u upon lambda cube over range 0 to 1. Now we have to put the upper and lower limit here. So first we have to put value of u as a 1 and then we have to put value of u as a 0. So if we put lambda u equal to 1 here, so we get 1 square sin lambda upon lambda plus 2 into 1 cos lambda upon lambda square plus 2 sin lambda upon lambda cube. Here we have to only replace that u by 1. So here 1 square, so here lambda into 1 is lambda only, here 1 into cos lambda because value of u is 1 plus 2 sin lambda because value of u is 1 here. So we get 1 square sin lambda upon lambda plus 2 into 1 cos lambda upon lambda square plus 2 sin lambda upon lambda cube minus, now we have to put the lower limit here. So we have to put here 0 square sin lambda u upon lambda plus 2 times 0 into cos lambda u upon lambda square plus 2 sin lambda 0 upon lambda cube. Now here 0 into anything is 0, so that term becomes 0. This term also becomes 0 because 0 into that term is 0 plus sin 0 is 0, so that whole term becomes 0. So this whole bracket term is become 0. So our final answer is sin lambda upon lambda plus 2 cos lambda upon lambda square plus 2 sin lambda upon lambda cube. That is our final answer. Now next is the suppose we have to find integration 0 to infinity e raised to minus u cos lambda u du. So that is the standard formula, e raised to ax cos of bx. So formula is that e raised to ax cos of bx is equal to e raised to ax upon a square plus b square in bracket a cos bx plus b sin bx. Here value of a is minus 1 and value of b is lambda, so we have to put here. So it becomes e raised to minus u upon 1 plus lambda square in bracket minus cos of lambda u, because here b is nothing but lambda, so a cos of bx, b is lambda and a is minus 1, so minus cos of lambda u plus b sin bx, so b is lambda, so lambda sin of lambda u, and limit of that integration is 0 to infinity. Now we have to put the upper and lower limit in u. We get e raised to minus infinity 1 plus lambda square into minus cos lambda u plus lambda sin lambda u. This is the finite term. If we put value of lambda infinity here, that is the bounded function, sin and cos are the bounded function. So here e raised to minus infinity is 0, so this 0 into whole term becomes 0. So 0 into finite term is 0 because of that whole term becomes 0. That minus because of the lower limit here we have to put, so minus e raised to minus 0 upon 1 plus lambda square in bracket minus cos of 0 plus lambda sin of 0. So cos of 0 is nothing but 1 and sin of 0 is 0. So here this term becomes 0 and this term becomes 1. So that minus and that minus become plus. So here we get, so whole that term is 0 minus that e raised to 0 is nothing but 1 upon 1 plus lambda square as it is, and that cos of lambda 0 is 1. So that minus sign as it is, minus into 1, that is minus 1, and value of that term is 0. So plus 0 is equal to that minus minus becomes plus, so 1 upon 1 plus lambda square. So that is the final answer. Okay, so thank you for watching this video.